So modeling nonlinear bivariate data. And just to bring this back, you do know or recall that linear growth is additive from your Algebra 1 days when you learned all about y equals mx plus b. And basically from one period to the next in your data sets for linear, things change in an additive way. So to illustrate that, this is some kind of task. Clearly it's not a real job because this is below minimum wage, but let's just say you're doing some kind of job that pays you $7 an hour, and if you don't work, you don't get anything. But if you work an hour, they give you $7, and if you work another hour, you get another $7. So it's additive. Every hour you work, they add on another amount of $7. So functionally, you could consider this to be f of h for hours equals 7 times h. So for each additional hour worked, $7 is added to a person's pay. Exponential is different. Remember the parent function, y equals a times b to the x. B is just a base. It could be 2 to the x, 3 to the x, whatever. But the input is going to be an exponent position and the output isn't. So what we see with exponential growth is that it's multiplicative. And that means that to go from one output to the next, you multiply by a common value every time. We're going to deal with exponential growth. So we're going to be looking for that multiplier value to be greater than 1 in each equal time period. Now this is important. I'm sure that there are other models that we could fit into exponential, but for our purposes we're really interested in time. Time being the explanatory and then whatever the outcome is being the response. If we were to multiply by a value between 0 and 1 for that common multiplier, we would not see the growth, we would see the decay. And that's great mathematically, but for our purposes, we're only going to concentrate on growth. All right, the first thing to do when you get bivariate data is to graph it. And whatever this is, it does seem to have an exponential behavior to it. But we're not really allowed to just go with our gut on this from just looking at a graph. We need to confirm this by checking for that multiplier, which we are going to refer to as a common ratio. That is a stats term. If we find it, then we can go and operate on the basis of it being exponential. All right? So looking at this, you see that we have equal time periods. All right? And you can also note that your explanatory variable does seem to have a linear sort of behavior to it. It's adding 10 every time. And it is complete, which is nice. In other words, they're not leaving out 1960 or 1980 or something like that. But you can tell here that from here to here is 13, and from here to here is, I think, 23, 24, I guess. But the point being that this is not additive growth. It just keeps getting bigger and bigger and bigger. So it looks kind of like we're setting up for exponential. So let's see how that common ratio works. What you need to do is don't start out with your first output, start out with the second one and put that in a fraction over the one that came before it. And you get, change it into a decimal and that's what you get. 91 over 67, keep doing that, and you get 1.35, and 122 over 91, and you just keep going until you run out of numbers. And then you look at what your ratios are, and these are remarkably similar. They're right around 1.35. Now, this is a little misleading because this common ratio does not have to be super, super precise from, one set of bivariate data points to another. But here they are, and so in order to get a snapshot of what that common ratio is, just average all those ratios. So we're looking at approximately 1.35 as what we would report as our common ratio. And let's go for it and call it exponential. All right, these numbers are always going to differ, or mostly are going to differ, because we're dealing with real world data, and there's always a little variation thrown in there that keeps this from being a perfect model. So speaking of models, let's go ahead and move on to our class example. So we'll close this out. Oh, hi. And let's go to this. And I have a different program to draw on. And this thing gave me an epic fail in my last attempt. So I just figure it's part of the learning curve. So hopefully I will not do it again. All right. Cell phone use. And here's year, time, number of subscribers. It does seem to be growing. We'll have to check to see if it's exponential. The first thing they want to do is for us to make a scatter plot in the grid. But let's start out in the calculator and go ahead and input this data, right? This data here into your calculator in, a spreadsheet. Call this year, call this subs for subscriptions. And note what I did. I did not put 1990 or 1993 or 4. I went ahead and just did this coded, right? It's quicker to deal with. Sometimes the older calculators would fall all apart. The TI-84s would do error messages or overflow outcomes, which are just a crash. But so just go ahead and do that. If you want to put the actual year in, it will probably work fine, but just go ahead and do it this way so that we're all on the same page, and I'll give you a second to do that. So pause. All right, I'll assume that you have everything set in here. So let's go ahead and do the scatter plot thing. So let's go to the home screen, and scatter plots are in your stats graphs. And remember, it's time, so year. That's usually explanatory, and number of subscriptions, and look, it does appear to have that curve to it, all right? So it could be exponential. Now the thing is, if I were to have given you data without 1990, if I just took this out, you might look at the rest of this and say, oops, it's linear. It actually is probably not, all right? It's just that you don't see as big of a curl in certain parts of the graph as you might otherwise see. So just looking at something and claiming that it's linear, it might not be. You never know. So our trick now is to go ahead and put this on here. So I'm going to go ahead and pause, but I'm going to ask that you not do that. Just wait till I come back. Okay, I'm back, and look what I did. Isn't this computer age just a wonder? It's a miracle. It's just a miracle. So, but my point here is I really kind of don't want you guys doing the graphing part. It's not going to be something you'll have to do on the AP exam. We're kind of beyond it for graphing. If you can just look at this in your calculator, yeah, we're fine. All right. So we'll just check off constructing a scatter plot. Now we're supposed to calculate the ratios of the subscriber values. All right, there is no way that we can make a common ratio with this and this. No way, because it's really not in equal time periods, right? Here we're missing 1991 and 1992. The rest of them are fine, right? So we're going to really need to start with this. Okay, so get back to my blue. And the way that you do that is to just take that 2,134, 24,000, let me get rid of that. All right, hold on. There it goes. All right, 24134. And that goes over the number before it, 16009. And that should give us 1.51. So then we go to the next one. That'll be 33,786 divided by that number before it, 24134. And that will give you 1.4. All right, I want you to go ahead and do the rest of those. I'm going to pause while I do it so that you don't get bored watching me. All right, so I'm back and I came up with all of these, and you'll notice that there is sort of a fairly wide discrepancy from where we start with this 1.51 to where we ended up with 1.24. But this is okay. This is all right. It's just regular data we're working with, and it's close enough. So if you add all those ratios up and average them, you get 1.325, and we'll call that our common ratio. All right, so let's just go with it. Let's just say the data is exponential. So yes, because it has that common ratio. All right, so what to do now? Let's go back to the calculator real quickly and look, you do have an exponential regression, which we could just go ahead and employ, but College Board wants us to do what they call linearizing this data. So we need to go back into here, so get into here, and what we're going to go ahead and do is straighten out this curvature, because really the curvature is coming from the response variable, not the explanatory variable. Remember, that's behaving sort of like linear. This is where the curl is coming from, or the curve. So let's go ahead, and what we want to do here is to take the log of subscriptions. So let's just call that LSUBS, if we can fit that all in. All right, and we want to put a formula here. We're just going to transform all of these into logarithmic values. All right, so let's go ahead and hit equals and control and x to 10 to the x to get log. You can do log base anything you want. College Board really likes natural log, but I'm just going to do common log here. So go ahead and put base 10 in there and scoot over, and we'll just put in the variable SUBS. Hit enter. And those are the logarithmic values for the number of subscribers, okay? And I think we're supposed to record those things, perform an appropriate transformation, show the transform values in the table above. That would be this table up here. So this column, I need you to write it down on your notes right in here. So let's see if I can do this right. All right, move this back down. Ah, I did it. All right, so I'm going to write those in, which means I'm going to pause for a moment. Let me get rid of this. And you put them in too. All right, so here they all are. And so what good was doing all of that? Well, if you go back to your calculator and go back to this, which was your scatter plot, let's go ahead and change number of subscribers to the log of the number of subscribers. It got pretty straight. Now, I know it's got a little bit of a bendy here, but this is straight enough for us to go ahead and do linear regression on it. So that's what we need to do. So let's go to the home screen and go to a calculator page, make sure everything is linked together, and let's go ahead and run that regression. So statistics, stat calculation, linear regression, a plus bx. All right, our x list is just going to be our year. The y list, since we're doing it as a linear, is the log of this number of subscribers. Keep this at F1, and let's just tab down to OK. And that is going to be our linear version of this exponential model. Okay, we can back transform out and get the regular metric for number of subscribers when we make predictions. It's all going to be good. But it's a linear model, and here's A, here's B, and note how strong R and R squared are. So if we can accept that this is linear, then it's pretty good linear. We do have residuals. We'll look at those later. So let's see what we've got back here. All right, back up here. I need to move this up. All right. All right, show the transform, then perform a least squares regression on the transformed data. Write the LSRL for the transformed data. All right, now normally we would start with y hat, but we're in transformed values, so it's really log y hat. This is a mistake. People leave the log part out, and this will be 3.7956 that's your A value, plus 0.13417x, all right? And just let's say x is going to be year from 1990. And let's just say y is going to be the log of the number of subscribers. I'm just going to abbreviate because I'm a little bit out of room. The correlation coefficient, let's just go back and double check. Remember, that's your R, 0.991163, so let's record that. And interpret what the coefficient of determination is telling you in the context of the problem. All right, let's just record that first. So R squared is going to be 0.982404. So 98.2% of the variation be careful, in the log, right, because we're still in logarithmic values, of the number of subscribers can be explained by the variation in the number of years since 1990. And you'll notice that it's following the usual script that we normally follow whenever we are doing this as a linear model. The only difference is this word right here. Whoops, made a little mark. This word right here in the log of the number of subscribers. All right, so yeah, let me get back to the blue. All right, so interpreting slope, the slope is this number right here. So this is going to be your B value, 0.13417. And so we can say for every increase of 1 year, since 1990, there is a 0.13417 increase, because it's a positive slope, in the log. Remember, we have to include that because that's what our outputs are, of the number of subscribers on average. On average. All right, sorry about all the writing. Just remember, you can always put any slope over 1 And so that's your change in y over change in x. So as each year increases by 1, you get that much increase in the log of the number of subscribers. All right? So let's go ahead, and I'm going to pause again because I need to change out. All right, I'm back. We're now on page 11, and they want us to work through the residuals, which I don't think I want to start out with. I think what I would rather do is go ahead and look at number 4 here, and then do the residuals last. That just seems to make a little bit more sense for me. All right, it says, use your model to predict cell phone usage in the year 1992. Would you feel comfortable using your model to predict cell phone usage for the year 2000? All right, so let's just start with the first thing here and call it number 1. And let's just rewrite this. So log y hat equals 3.79563 plus 0.13417. And 1992, remember we coded this. This would be year 2. So let's put a 2 as our input. And let's get this down to one number. So log y hat equals 4.06397. All right, let me get rid of that. That doesn't look much like a 7. And that is really not a number of subscribers, because our subscribers were in the thousands. Our smallest number was, I don't know, over 5,000. But this is actually not a subscriber. It is an exponent on base 10, which would then produce the number of subscribers. So let's go ahead and put both of these things on base 10. So here's base 10 log, and remember that is base 10 of y hat equals 10 to the 4.06397, right? And remember, when this matches this, the argument drops out, and 10 to this number is 11,587 subscribers. All right, so in 1992, we would expect 11,587 subscribers. And if you look back, that should fit in those, between those first two values, the first one being 5,283, and then the next one is 16,009. So that seems reasonable. Looks good. All right, so as far as predicting for the year 2000, our domain only goes up to 1999. So we're looking at trying to predict beyond the domain, and that's not good. So basically the answer to this is 1 shouldn't predict for the year 2000. As it is an extrapolation. And such predictions are unreliable. All right, sorry about the terrible handwriting, but you get the idea. All right, so yeah, we're employing the same techniques that we knew with linear to this. Okay, so the last thing to do is residuals, and let's go to the calculator, and that's a very, very quick thing to do. So if we go to here, and here's the trick I usually use, control and arrow up, and then just go wherever I want to go. Let's say here, and hit enter. There we are. You probably have your own trick. Let's go ahead and change this. Since our model, our linear model, is based on logarithmic values, we can go ahead and change this to stat resid, because that model is linear, okay? All right, now here we go. This has got a completely different interpretation for what we have in linear, regular linear. The issue here is not the fact that it's curved. That's not an issue, all right? You can't just say, oh, the model doesn't apply because it's curved. All we want to do is identify years like this one, and this one, and this one that are below that 0 line. So we were seeing growth in these 3 years that are happening slower than the model predicts, all right? These 5 all being above the 0 line, this is where growth in our model is occurring faster than the model predicts. All right? This one is pretty close to actual what the model would predict, but it's still above the line. So 1993, 4, 5, 6, and 7 are all years where growth in cell phone subscriber or subscriptions are occurring faster than the model predicts. And then 1990, 1998, and 1999 are years where growth in cell phone subscriptions are occurring slower than the model predicts, or more slowly. So they want us to go ahead and put that in our notes. So I am going to pause and pull off some more magic. All right, so through the magic of computer software, I went ahead and pasted that particular residual plot into the notes, which I'm not asking you to recreate that residual graph by hand, just like the graph on the front page. And I'm not asking you to sit through the explanation of what the residual graph shows you, but I did write it out so you can pause and copy it. Basically, I just highlighted the 3 years where we saw growth below what the model predicts for subscribers, here, here, and here. And then the other years are showing faster growth in subscribers than the model predicts. That's all that you use a residual plot for when you're doing an exponential model. So that's your notes. I'm sorry.